In the last lecture, we looked at the early developments of mathematics in Mesopotamia and in Egypt. With this lecture, I'm beginning a series of 3 lectures that look at Greek mathematics. And the Greek world, the Hellenic and Hellenistic worlds would dominate mathematical development for basically 1,000 years, from about 600 BC until around 400 AD. I'm going to focus in this lecture on the first 300 years, from about 600 right up until around 300, and something very important happens around the year 300, and that is when Euclid of Alexandria writes his great books. He's best known for the Elements, which is often considered to be a work of geometry. It actually has much more than geometry. It really covers much of the mathematics that was known at that time. And between the Elements and the other books that Euclid wrote, they really cover everything that was known in the Greek world. And for that reason, nobody bothered to keep any of the earlier Greek texts in mathematics. Euclid was so successful in summarizing what everybody else had done that there was no point in keeping what anybody else had done. Incidentally, it's not clear how much of the mathematics in the writing of Euclid really was his own. There are some people who believe that he did not discover any mathematics by himself, that none of the theorems in Euclid's work really are original to him. There are other people who do argue that certain pieces of it he must have been the first to come up with. But what is significant about Euclid's Elements, written around 300 BC, is that they do summarize what was known before, and they set the foundation for everything that would come afterwards. The earliest of the Greek mathematicians that we know something about is Thales of Miletus. He was born in the late 7th century and then would go into the 6th century. Thales was interested in a number of problems related to finding distances between objects. We know that Thales studied with the Egyptian mathematicians, that he picked up much of their mathematics. He did learn astronomy from them, and it's been recorded that he predicted the eclipse that occurred in the year 585. It's also been recorded that he was able to calculate the height of the pyramids. He would have used similar triangles in some way. It's also been recorded by Plato that Thales came up with a way of determining the distance that a ship is offshore. If you've got 2 different points on the shoreline and you're able to observe the ship from both of these points, you can then do a geometric argument that enables you to determine the distance out to the ship. Plato also records one of the events that apparently happened to Thales, and it illustrates the concept of the absent-minded mathematician. Thales apparently one night was walking along studying the stars when he fell into a ditch, and a young servant girl who happened to be nearby pulled him out and asked him, "How is it possible for you to understand what is going on up in the sky if you do not even see what is at your feet?" Thales of Miletus sets an important example for Greek mathematics because of his fascination with the idea of distance, calculating the heights of the pyramids, figuring distances out to a far ship. You're using geometric ideas, and certainly the other kinds of ideas of mathematics will appear within the Greek tradition. There is a lot that is built on problems of commerce, problems of taxation, as well as astronomy. But it's these geometric problems that really will come to dominate Greek mathematics. And we're going to see that in a very large dependence on the idea of ratio and proportion. So ratio, taking the ratio of 2 integers, so one integer divided by another, and working with those ratios of numbers. Very often, instead of working with pure numbers, what the Greek mathematicians would do is to work with ratios. And we see this particularly strongly in the work of Pythagoras of Samos. Pythagoras was born sometime around 580 BC. Samos is just a stone's throw from Miletus, and it is believed that at the very least he probably met Thales. There is a tradition that he may actually have studied with Thales, but we do know that Pythagoras learned much of his mathematics by traveling to Egypt, and he actually was indoctrinated into many of the mystic practices of the Egyptian astrologer priests. He learned a lot of the Egyptian astrology or astronomy or mathematics at this time. He happened to be in Egypt at the time that Cambyses of Persia conquered Egypt, and Pythagoras was taken back to Babylon by Cambyses, and he took advantage of this. There was still a very strong mathematical tradition in Babylon at this time, and according to the tradition, Pythagoras learned a great deal of the Babylonian mathematics, the Babylonian astrology or astronomy at this time. After leaving Mesopotamia, after leaving Babylon, Pythagoras went to Italy, and there he founded his own school, what became known as the Pythagorean school, or sometimes the Pythagorean cult, because he really adopted many of the cult practices, both of the Egyptian and also of the Babylonian or Mesopotamian mathematicians. He set up a group that was very mystical, very secretive. We don't have many details of exactly what was going on in this group, but we do know, certainly according to tradition, that Pythagoras believed that mathematics lay at the core of all nature. The quote that Plato ascribes to him is that at its deepest level, reality is mathematical in nature. There certainly were cultish aspects of the Pythagoreans. They followed the Egyptian priests' practice of never eating beans, never wearing leather, but they also were clearly interested in developing the mathematics, and in particular developing mathematics built around ratio and proportion. And so music and the musical scale, which is very much built on ratios, is something that is generally attributed to the Pythagoreans. There are developments in architecture and the kind of proportions that you should have as you design buildings that is often attributed to the Pythagoreans. And of course, the Pythagorean theorem is often attributed to them. As we know, the Pythagorean theorem is much older than the Pythagoreans, but in fact they appear to have been the first people to actually come up with a proof of the Pythagorean theorem. This is more than an observation that the areas of those two squares on the legs is equal to, when you add those two areas, it's equal to the area of the square on the hypotenuse. That according to tradition, it's the Pythagoreans who actually came up with a proof of this fact. The Pythagoreans are also credited with coming up with the idea of an irrational number, that there are numbers that cannot be represented using fractions. They cannot be represented using a ratio of two integers. And the first example that we know of this case is the square root of 2. The square root of 2 is about 7/5, but it's not exactly 7/5. And in fact, you cannot find a fraction that's exactly equal to the square root of 2. We don't know when this was first proven. It is often attributed to Pythagoras himself. And one of the stories that is out there is Pythagoras discovered this fact, and there was a great feast among the Pythagoreans. Another one of the traditions is that it was one of Pythagoras' disciples who discovered this fact. And there was a great celebration that was experienced around this. And a third tradition is that it was one of Pythagoras' disciples who discovered that the square root of 2 was not a ratio, that it could not be represented as a ratio of two integers. And Pythagoras was so disappointed and upset at this revelation that he banished this disciple from among the Pythagoreans. The next mathematician I want to look at is Zeno of Elea. This is in what today is Italy. He's a 5th century mathematician, and he's best known for his paradoxes. He was interested in this whole question of what it means to consider all possible distances and assign a number to any possible distance. It's what today we refer to as the continuum. Does every single point between here and over there actually correspond to some number? If it does, then you start to get some paradoxes coming in. I want to focus on just one of them because it's going to be important later on when we get to calculus. And that is the problem if you consider an arrow in flight and you look at how fast it's traveling. That's its velocity. And you can determine the velocity by looking at how far it travels and how long it takes to get there. So the distance that it travels divided by the time that it takes to get there is its velocity. Well, if every single point between here and the end point of the arrow's trajectory is a number, we can think about what's happening to the arrow when it reaches a specific point. When it reaches a specific point in time or in distance, what's going on there? Can we assign a velocity? Well, it seems to Zeno that we can't possibly assign a velocity because if we're looking at the arrow at one instant, it doesn't travel any distance. And if it doesn't travel any distance, it can't possibly have a velocity. So at any instant in time, the arrow is not moving. But to get from here to there, we've got to pass over the continuum. We've got to pass over every single point. And at each point, the arrow is not moving. And if at each point the arrow is not moving, how does it succeed in getting from where I shoot it to where it lands? That's one of Zeno's paradoxes, and it would take a long time to really begin to grapple with this. Aristotle, in the 4th century BC, would be one of the people who attempted to work with Zeno's paradoxes by essentially banishing them. What Aristotle did was to separate mathematics into those numbers that are proportions and deciding that we could work with them, and then the continuum that also contains these strange numbers like the square root of 2 that cannot be represented by a ratio, and simply put them into a whole nother category. There are other separations that Aristotle makes that turn out to be very significant for the development of mathematics. And one of those is the difference between arithmos and logos. Arithmos is the origin of our word arithmetic, and so Aristotle is looking at basic arithmetical calculations, the kinds of calculations that would be used by people doing commerce or that would be used by the scribes and the civil servants, versus the kind of logical mathematical argument, the close reasoning that I talked about in the very first lecture, and that he referred to as logos. And logos is an interesting word. It literally means word. And in the ancient Greek world, this word logos carried many, many different meanings. And in fact, in the opening lines of St. John's Gospel, we have the word logos used, and archein o logos. In the beginning was the word, but you could interpret that to refer to Aristotle's sense of logos. In the beginning was logical mathematical reasoning. I don't think that's quite what St. John had in mind when he wrote this, but it's interesting food for thought, and it certainly fits into much of the Greek tradition, and especially the tradition of the Pythagoreans. The next mathematician that I want to look at is Theaetetus of Athens, born around 417 BC, died around 369 BC. He was a friend of Plato. He was at the Academy in Athens. Theaetetus did a number of important things that would be reflected in the work of Euclid. In particular, Theaetetus is considered to have been the mathematician who finished the description of what today we call the Platonic solids. They are named for Plato, but they certainly do not come from Plato. So these are solids that have faces that are flat, and the faces are all regular polygons. So, for example, a cube is a simple example of a Platonic solid. So each of the sides of a square, each of the sides of a cube is a square, so a regular four-sided polygon. There are other examples of Platonic solids. There is the tetrahedron that has four sides. Each of the sides of a tetrahedron is an equilateral triangle. Another example is the octahedron that is made up of 8 triangles. And there is the dodecahedron that is made up of 12 pentagons. There is another Platonic solid. The tradition in Greek mathematics was that the Platonic solids came from the Pythagoreans, but almost certainly the last of these was not known to the Pythagoreans. Almost certainly it was originally discovered by Theaetetus, and that's the icosahedron. And this is a solid that is made up of 20 triangles. So the faces of this solid are made up of equilateral triangles. Something else that Theaetetus did was to work with the question of how do you recognize a rational number? One of the problems that we have when we're working with rational numbers is that you can have two very different appearances to the same rational number. Thus, 3/4 is the same as 6/8, which is the same as 12/16. Now, in those cases, it's easy to see that they are all the same fraction. But what if you've got a more complicated fraction like 119 divided by 91? What's the simplest way of expressing that? And it's not clear if this idea originally comes from Theaetetus, but he certainly exploited this. And this is the idea, if we're thinking about the fraction 119 divided by 91, to first look at what's the largest integer in that. The largest integer in that is 1. How much is left over? 28 over 91. Now, once you take out the largest integer, whatever is left over is going to have to be a number between 0 and 1. Let's take its reciprocal. Instead of 28 over 91, we look at 91 over 28 and find the largest integer in that. 28 goes into 91 3 times. What's left over is 7 over 28. Let's repeat that process and take the reciprocal of 7 over 28. That's 28 over 7, and 7 goes exactly into 28 4 times. If you start out with a rational number and you do this process, take out the largest integer, look at what's left, take its reciprocal, take out the largest integer, that's going to stop after a finite number of times, and you can now redo this process. The integers that we got were 1, 3, and 4, and we can back up. Start with 4, take its reciprocal and add 3 to that. That gives us 13/4. Take its reciprocal, 4/13, and add 1 to that. That gives us 17/13. And that gives us the original pair in their reduced form. 119 over 91 is equal to 17 over 13. This is what would come to be known as the Euclidean algorithm. And what Theaetetus realized was that he could prove that the square root of 2 was not equal to a rational number by showing, and this is a geometric argument that unfortunately I don't have time to go into, but he used a geometric argument in which he showed that if you take the side of a square plus its diagonal and ask how many times does the side of the square go into that, well, it goes in 2 with a little bit left over. And geometrically, Theaetetus was able to show that if you take that little bit that's left over and you look at its reciprocal, that's exactly the number of times that the side of a square goes into the side of the square plus its diagonal. So that if we're trying to take the side of a square plus its diagonal, 1 plus the square root of 2, that's equal to 2 plus a number whose reciprocal is what you started with. 2 plus 1 over, 2 plus 1 over, 2 plus 1 over, 2 plus 1 over, and so on. This continues forever. It never terminates. This cannot be a rational number. Incidentally, this gives you a very accurate way of approximating the square root of 2, is to work this process backwards. Start with 2, take its reciprocal and add 2. 2 plus a half is 5/2. Take that reciprocal and add 2 to it. That gives you 12/5. Take its reciprocal, 5/12, and add 2 to that. That gives you 29/12. Take its reciprocal and add 2 to that. That gives you 70/29. Take its reciprocal and add 2 to that. You get 169/70. And I hope you see how you can continue this as long as you want and get as accurate as you want. But if I take 169/70, that accurately measures 1 plus the square root of 2 to an accuracy within 1 in 34,000. And you can quickly get whatever accuracy actually is needed. The next Greek mathematician I want to look at is Eudoxus of Cnidus, also someone who was at the Academy in Athens. He was born sometime between 395 and 390 BC. Eudoxus of Cnidus was interested in this question of how do you define an irrational number. If you've got a number like the square root of 2, we've seen how Theaetetus was able to take the problem of when are two rational numbers equivalent to each other and working out a procedure for deciding that. And what we're looking at here with Eudoxus of Cnidus is how do you decide if two irrational numbers are the same? And he came up with a brilliant idea that actually would be adopted in the 19th century of the modern era by Richard Dedekind, that we'll be talking about much later. The way to compare two irrational numbers and decide if they really are the same number is to look at the rational numbers that are larger than each of them. And if every rational number that's larger than this irrational is also larger than the other one, and if every irrational number that's smaller than this is also smaller than the other one, then the two irrational numbers have to be the same. This is an idea that Euclid would pick up, and he would use as an important foundational aspect for studying all numbers, whether they are rational numbers, in which case he would explain what we call the Euclidean algorithm for deciding when two rational numbers are the same, or for comparing the size of irrational numbers. Eudoxus of Cnidus is also important for his work on areas and volumes, and he is credited with being the first mathematician to really work out how to take this problem of finding the area of an irregular region, or taking the volume of something that's not just a rectangular solid, and approximating the area by chopping it up into little rectangles or little rectangular blocks. And so this is a method that would come to be known as the method of exhaustion. Euclid describes it in his writings, and in the next lecture I'm going to talk about how Archimedes of Syracuse really refined this idea and turned it into a very powerful way of working with the problem of finding areas and volumes. Euclid of Alexandria is a shadowy figure. It's generally believed that he lived roughly from 325 to 265 BC. But the fact is, not only do we not know when he was born or when he died, we don't even have any definitive proof that he ever existed. There is no contemporary who wrote about him. There is a reference in one of the works of Archimedes, but a lot of the scholars believe that that was a later edition. We don't get the first biography of Euclid until 750 years after he lived. However, there is a body of mathematical work that was written around the year 300 BC that clearly was all written by the same person. It's in the same voice with the same kinds of ideas and the same logical development. Somebody must have done this writing, and we might as well believe that it is the person to whom it's attributed, this Euclid of Alexandria. Now, Alexandria is a city that had been founded after the death of Alexander. The first ruler of Egypt following the death of Alexander was Ptolemy I, and he built a center for scholars, what was known as the Museum. This was a temple to the Muses. It's the origin of our word today, museum. And the Museum was set up by Ptolemy I in the last years of the 4th century BC to be a center for scientific work, for scholarly work. And there was a group of mathematicians who were pulled together at the museum, and Euclid almost certainly was the person who was leading this group. And his job was to take the mathematics that was around him and condense it, explain it. And while we're not sure how much of this mathematics was original to Euclid, what was very original to Euclid was the way in which he was able to explain the mathematics and put it on a very logical foundation. Euclid clearly made important choices about what needed to be defined and how it would be defined, what needed to be taken as a postulate or assumption or axiom, and how these then would be structured into proofs. Euclid was one of the greatest teachers to have ever existed. Euclid should be thought of as a great textbook writer. And that's really what's going on here. He is taking ideas, most of which existed in Greek mathematics before his time, and he is organizing them in an incredibly effective way. Euclid's Elements is still a textbook that is used today. It has gone through well over 1,000 editions in many, many translations. And it's made up of many books. It's usually, when you think of Euclid's Elements, you think of geometry, and the first 4 books of Euclid's Elements really are devoted to geometry. But there's much other mathematics that's going on here in addition to that. Books 5 and 6 deal with ratio and proportion. Those books are also looking at similarities in geometry. Books 7 through 9 look at number theory, and here is where Euclid explains this Euclidean algorithm that really comes to us from Theaetetus, or possibly even earlier than that. Euclid looks at sums of geometric progressions. This is where Euclid proves that there are infinitely many prime numbers. So a prime number is one that is only divisible by 1 and itself among the positive integers. And Euclid proves that, in fact, there are infinitely many such primes, 2, 3, 5, 7, 11, 17, and so on. Book 10 of the Elements looks at the meaning of irrational numbers. And here is where he picks up this idea of Eudoxus of Cnidus on how to define an irrational number. And Book 10 talks about how to compare various kinds of magnitudes. And chapters 11 through 13 look at solid geometry. He explains Eudoxus's method of exhaustion, how to find areas and volumes of irregular objects. He explains how to construct the Platonic solids. And he goes well beyond that. He doesn't just explain what the Platonic solids are. He actually proves that these are the only ways that you can construct a solid so that all of the faces look exactly the same, and that all of the faces are in fact regular polygons, polygons in which all of the sides have exactly the same length. There's much else that Euclid wrote. He also wrote 2 other books on geometry. We still have some pieces of those, one called Data, one called On Divisions. He wrote one of the first books on optics, and in that book we find the very first recorded treatment of the question of perspective. Another one of Euclid's books is a book on astronomy called Phenomena. And there are several other books that people recorded that Euclid had written, but unfortunately which no longer exist. There is one book on surface loci, so this would be 2-dimensional curves. There's another book with an intriguing title, Porisms, and people are not quite sure what is meant by a porism, but from some of the examples that other people make of the kinds of results that Euclid stated in this book, these appear to be results that can easily be deduced from other theorems that he proved. Most of the porisms are geometric results that follow from the main theorems that Euclid proved in the Elements. There is also a book on conics. There is a book that's called the Book of Fallacies, and he had at least one book on music. For the next time, we're going to look at the following 700 years of Greek mathematics. from the time of Euclid right up until about 400 AD. We're going to focus in particular on Archimedes. We'll also be looking at Apollonius, Diophantus, and the first recorded woman in mathematics, Hypatia of Alexandria.